This is unit 1.10 and we're looking at electrolysis in this topic. And we started electrolysis off yesterday by watching a short video, and I've put the link to that in the comments box, so it would be worthwhile having another look at that video, another watch at that video, just to explain the whole process of electrolysis. The little bit in the middle, it's not the whole video that's appropriate, but the little bit in the video about lead bromide, the electrolysis of lead bromide, that will be particularly helpful to you. But if you have your notes in front of you, we'll have a work through this topic. So as I said yesterday, electrolysis is all about splitting up ionic compounds into the elements that make them up. And if we even have a look here at this word electrolysis, the word lysis means to split something up. So to be split up. The word electro then means it refers to electricity. So literally the word electrolysis means splitting up something using electricity. And that's exactly what we're doing. We're taking an ionic compound and we're splitting it up into the compound, or to the elements that make it up, and we're doing that using electricity. Now, before we make a start, I want to remind you of these two definitions. Firstly, of a cation, and then secondly, an anion. It's really important that you keep those definitions in mind as we go through this. There's one part of it that makes it slightly tricky to get your head around, but if you keep these definitions in your head, it will really help you. So a cation was a positively charged ion. It might have a charge of 1+, 2+, 3+, but it has to have a positive charge. An anion is a negatively charged ion. Okay, so cation positive, anion negatively charged ion. Before we move on at all, we want to have a little look at some definitions here. And there's 5 of these, and you do need to know these definitions, but actually understanding them is even more important. So what is electrolysis? Well, I've already said that it's splitting up a compound using electricity, but the exact definition that we want is that it's the decomposition of a liquid electrolyte using a direct current of electricity. So it's a little bit more complex than just saying splitting something up using electricity, but it's the decomposition of a liquid electrolyte. And I'll explain what an electrolyte is in a second. Using a direct current of electricity. So next up we'll have a look at that word electrolyte that we met in the first definition. So what is it that an electrolyte is? Well, an electrolyte is a liquid or a solution that conducts electricity and is decomposed by it. That's the definition of it. So an electrolyte in electrolysis is the liquid or solution that conducts electricity and is decomposed by it. Again, that won't make an awful lot of sense at the minute. It will make more sense when we look at electrolysis, but it's the idea we've got something, a liquid that is able to conduct electricity. First of all, that's essential, and we saw that in the video yesterday, but also it's the fact that electricity is able to break an electrolyte up. Okay, so what's in an electrode then? Well, electrodes are these things that we can see in the diagram up here, and the sort of dark grey rectangles that we have at the top here. So this is an electrode, and specifically this is called the cathode, and then the one on the right here is labelled as the anode. But these two grey bars, they are called the electrodes. And what the electrodes are they are there to conduct electricity. So basically what we'll see is that we've got a complete circuit here. So if we've got my solution, if we colour the top of that blue, that's my solution, and you can see that my ions are in my solution. And because this liquid can conduct electricity, what I see is that there's a complete circuit between the wires, the electrodes, so the electrodes can conduct the electricity, into the solution. If the solution can conduct electricity, then I've got a complete circuit here. So the electrodes they're inert rods. We describe them as, what that means is they're just unreactive. They're unreactive rods and that are used to conduct electricity, they're used to conduct electricity within the solution and to separate this solution out into the different components. So the definition is they are inert rods that are used to conduct electricity. And are unreactive. And usually they're made out of graphite or platinum. Normally graphite or another unreactive material, for example platinum. Okay, so if you can remember back from our structures topic, we saw that graphite is able to conduct electricity because of the delocalized electron within the layers of the graphite. So that's why we can use graphite, and it's fairly unreactive. So it can conduct electricity, which is the most important thing, and it's unreactive. Platinum also is a metal, obviously, and so it can conduct electricity, again, by those delocalized electrons that are within the metal structure. The reason we normally use graphite is simply because it's cheaper than platinum, but platinum can be used as well. Okay, so we've mentioned the anode and the cathode, and what we find with the anode is that it is the positive electrode, and with the cathode, yes, it's an electrode as well, but it is the negative electrode. And when I put these definitions up on the board, I always have people saying to me, "Miss, you got that the wrong way round." Because they say to me, an anion is negative, and so why is the anode positive? Well, we'll see why that happens, but it's that idea that opposites attract. So if you've got an electrode that is positive, the anode, it is the anions that are attracted to it. And that's why we see it's kind of the opposite way around here. So that's really essential that you remember. So it's maybe worth highlighting that that fact that the anode is positive and the cathode is negative. That's kind of counterintuitive to what we've done so far. So yes, an anion is negative. You'll see that up at the top of the page. But the anode is positive, the positive electrode. And that'll make a wee bit more sense in a second. Okay, and there's just a couple of notes down there. We've already mentioned graphite is used as the electrodes. And also the electrolytes that we use, they're usually molten ionic compounds, because that's really our aim with electrolysis, is we want to take ionic compounds and split them up. And also aqueous ionic compounds. So if we dissolve an ionic compound in water, we can also use it as an electrolyte to conduct electricity. Because if you remember, ionic compounds, they conduct electricity when they're molten or in solution. And that's what just the second point is mentioning there. So how is it that electrolysis works? Well, what we have with electrolysis is we have ionic compounds. And if you think about the structure of ionic compounds, they're in a lattice structure. So I'll just draw a quick lattice structure here. And we have positive ions and we have negative ions. And they're all stuck together in a lattice structure. But what happens when we melt them or when we dissolve them in water is that those ions become free to move and carry the charge. So they're all spread out a little bit. And actually then they can move past each other and are free to move and carry the charge. So remember, for something to conduct electricity, it needs to be a charged particle that is free to move and carry the charge. Our ions are charged because they have either a plus or a negative charge. and they're free to move and carry charge when they are molten or when dissolved in solution, but not when they're a solid. Okay, so how does electrolysis work? Well, if you think about it, ionic compounds are made up of ions, with positive and negative ions. So first of all, we've got our negative ions, and they are called anions. And try not to get mixed up with this as we go along. And what happens is, in the ionic solution or the molten ionic compound, the anions, the negative ions, are attracted to the positive electrode. And if you think back to our definition, the positive electrode is the anode. Okay, and it's this idea that's really important, is that opposites attract. That's why the anions move to the anode. In our ionic compounds, we'll also then have cations as well. And the cations move towards the cathode. And that's because the cations are positively charged and the cathode is negative. And so those positively charged ions are going to be attracted to something negative. And that is called the cathode. So right throughout this topic, I want you to be saying to yourself, anions go to the anode, cations go to the cathode. So what is it that actually happens when the ions get there? Well, at the anode, we've got the anions moving towards there. So think what we have here. We've got the anode is a positive electrode. So we'll write some positive charges here. And what happens is that the negative ions come and they are attracted to that. Because the ions, the anions are negative, what that means is that they have an excess of electrons. So if you think for something to be negative, it must have more electrons than protons. And so what happens at the anode is that the anions, they give some of their electrons to the anode. Okay, so if they give electrons to the anode and they then become neutral overall. So they lose their negative charge and they become atoms. When they have an overall charge of neutral, that's then back at atoms. And for example, sometimes we have things like bromine or chlorine that are diatomic. And so what we find there is at the anode that we form maybe 2 atoms of chlorine and that they then join together to form a diatomic molecule. But don't worry too much about that for now. But at the anode, basically the basic thing you need to learn is that the anions move towards the anode, they lose electrons and become atoms. At the cathode, it's the exact opposite. So obviously our cathode is the negative electrode. So it's a negatively charged electrode. And so that means that the cations are attracted to it. Remember, opposites attract. And the cations are positively charged because they have more protons than electrons. So in order to get back to atoms, we want to even that out. We want the same number as protons as electrons. And so what we find in this case is that actually the cations pick up electrons from the cathode. They pick up electrons and they become atoms again. Okay, so with cations, remember that they have more protons than electrons. We want to balance that out. And so it has to accept electrons to become overall neutral again. Over on the next page, you have a typical diagram of the apparatus that we use for electrolysis. This would be sort of on a lab scale, a smaller scale. And you may be asked to draw this apparatus, so it's worth drawing, or you may be asked to label it, or you may be given it and asked to explain the process of electrolysis, which we'll look at a wee bit more now. But this is apparatus that you need to be familiar with. And conventionally what we do is we draw the anode, and that's the positive electrode on the left, and the cathode on the right, which is a little bit different than on your diagram on page 3. But this diagram here in front of you, that's the one you want to focus on. Anode on the left, cathode on the right. It's not always drawn that way, but conventionally that's the way we do it. Okay, so there's two ionic compounds that we're going to look at specifically, and that is lead bromide and lithium chloride. For these two examples, you need to know the specific observations at the anode and the cathode, and you also need to know what we call half equations. Half equations, or sometimes they're referred to as ionic equations, and it would be worth making a note of that, that half equations are sometimes referred to as ionic equations. Half equations is a more accurate description of these equations, because a half equation, what it does is it shows us how an atom or an ion gains or loses electrons. It shows that kind of movement of electrons, and we'll see that with these examples of lead, bromide and lithium chloride. So over on page 6 we have a simplified version of the apparatus for the electrolysis of lead bromide, and you can see a bit of what's happening here, and this will be helpful for when you're revising through your notes. But what I want to do is just take this from scratch and look to see what is actually happening here. So the first thing to think of when you're looking at electrolysis of a particular compound is to think about the ions that make up the compound. And we did a little bit of practice of this when we were writing our ionic equation. So we have lead bromide, and the formula for that is PbBr2. And you should be able to write that. Now let's think about the ions that make that up. Of course, our metal is lead, which is Pb. And our non-metal is bromine, which is Br. I have to think to myself, what charge does a lead ion form? And you might be tempted by your periodic table to see that it is in group 4, and so might think it forms a charge of 4+. But actually we find that lead forms ions with a charge of 2+. And we can see that from the formula of PbBr2, but also if you look at the back of your periodic table, so if you haven't got it out in front of you, please do get it out. On the back of the periodic table, under the positive ions, you'll see down towards the bottom there's lead, and it's given to you as Pb2+. So the charge of lead is Pb2+. Then bromine, and we know that it's Br. And we know that it is in group 7, and group 7 all form charges, ions with a charge of 1-. So we've got Pb2+ and Br-. In ionic compounds, the charges always have to cancel, and that explains why we have 2 bromine ions. And so I just put a 2 in front of my bromine. Okay, so what actually happens in my electrolysis? Well, the first thing to think about is the fact that I have in my solution, or in my molten ionic compound, I have freely moving lead ions and bromide ions. And they are free to move about within the solution. Okay, what happens is when we pass electricity through these electrodes is that the ions start to become attracted to the electrodes. So anode, first of all, let's look at it. What is the anode? It is the positive electrode. It is the positive electrode. So it's not my positive ions that are going to go to it, but rather my negative ions. Remember, anions go to the anode. So what I find is that the bromide ions come to the anode, the negative or the positive electrode. And I have to think to myself, what does bromine need to do to get back to an atom? What does bromine need to do to get back to an atom? Well, at the minute, it's got a charge of -1-, because it has 1 more electron than it does protons. It has 1 more electron than it does protons. And so what we find with bromine is that it loses that electron. It loses that electron into the electrode, and then it becomes an atom. And as a bromine atom, we know that it has no charge. It has no charge. So let's think about an equation that we could write to represent what has just happened. So what we've started with is a bromide ion, a negative bromide ion, and it has lost an electron. I can represent that by saying minus electron. And in half equations, we have to show electrons as the symbol E minus. E minus, you have to include that little minus charge there. So that is E minus. Okay, once it's lost an electron, it then becomes a bromine atom. So simply a bromide ion losing an electron and becoming a bromine atom. But we know about bromine that it doesn't just exist as Br. We know that it exists as Br2. And so in order to form Br2, think about what we have to do. In order to form Br2, I need 2 bromide ions. So I start with 2 bromide ions. Each of those bromide ions is going to lose an electron. So if each loses 1 electron each, they lose a total between them of 2 electrons. And so this is the half equation for what happens at the anode. Yes, ultimately I have a bromide ion losing an electron to give me a bromine atom. But we know that bromine's not happy on its own. It likes to form diatomic molecules. So I need 2 bromide ions losing 1 electron each, so that's a total of 2 electrons lost, to give me a bromine molecule, a diatomic bromine molecule. And that half equation is what you need to know, and it's what we'll be writing into our notes in just a second. Okay, so what about the cathode? Well, the cathode is completely opposite from the anode because it is negatively charged. So what's going to be attracted to it? If it's negatively charged, then it's going to be the positive ions that are attracted to it. In this case, we've got our lead ions that are attracted to it. So our Pb2+ ions. Okay, so Pb2+, what that means for lead is that it has 2 more protons than electrons. 2 more protons than electrons. What I need to do is I need to balance that out. And the only way that I can do that is by lead gaining 2 electrons. So what it does is that it gains 2 electrons. So 1 electron from here, and then maybe 1 electron here. So lead gains 2 electrons to try and get back to a lead atom. And that's exactly what happens. The lead ion then becomes a lead atom after it has gained 2 electrons, and that's what's happened here. So let's think about an equation that we could use to represent this. So over on the right hand side with the cathode, we've started with a lead ion, which is Pb2+. It has gained 2 electrons, and I show that by writing plus 2 electrons. That shows it's gained 2 electrons, and that it has become a lead atom. And lead is not diatomic or anything like that, so we can just leave it as this is the equation that you need to know for the cathode, the reaction that happens at the cathode. So you can see that over on the left, I've got my anode, and what has happened there is that bromine has lost an electron. The bromide ion has lost an electron to become a bromine atom. And over on the right-hand side, the lead ions have gained 2 electrons to become lead atoms. So overall, this is kind of the opposite to bonding. What we're trying to do is, rather than forming ions, what we're trying to do is get back to the normal atoms, get back to the atoms that have no charge. And what we find with this is that there's a wire that connects these 2 electrodes. And if you can see what's happening here, and I'll go over it in blue here. What's happening is the bromide ions are coming to the anode. They're losing their electrons into the anode. And what's happening is that the electrons are moving around the circuit. And then it is actually the lead ions that are picking up those electrons, gaining those electrons so that they can become a lead atom. So overall, you can see that this circuit is complete. Bromide ion is giving the electrons in to the electrode. They're moving around the circuit from the anode round towards the cathode, and then the lead ions can pick them up. So let's go back to page 6 and fill in our notes with this information. So let's recap what happens at the anode in the electrolysis of lead bromide. Well, first of all, what I need to do is work out what the anion is. So remember, the anion goes to the anode. So what is my anion? Well, it's my bromide ion, Br-. What half equation can I use to represent it? Well, because it's negatively charged already, I need to lose electrons. So I've got my bromide ion, and because it's got a charge of 1-, it needs to lose 1 electron to become a bromine atom. But what we said with this is that bromine doesn't like to exist as an atom. it likes to exist as a diatomic molecule, and that's Br2. So in order to form Br2, I'm going to need to start with 2 bromide ions. And because I've got 2 bromide ions, each losing 1 electron each, I have a total of 2 electrons lost. So just in case that's not clear, what you should have written, I'll rub that out and do it over again. What you should have written in there is 2 bromide ions that lose 1 electron each, which is a total of 2, to give me Br2. And that's the half equation that you need to know for the electrolysis of lead bromide. And that's the half equation that happens at the anode. You also need to know what your observations are. And for the observations, the best thing to think about this is just, what am I producing? What is on the right hand side of my equation? It's as simple as that. So I am forming bromine. And because the temperatures used in electrolysis are so high, what we find is bromine is actually a gas. So normally at room temperature it's a liquid, but because the temperature needs to be so high to melt down our ionic compound, we'll talk a wee bit about that later on, bromine is actually a gas. So what I need to think to myself is, what colour is bromine? And you should know from your Unit 1.3 periodic table notes is that bromine is a red-brown liquid. But because it's a gas in this state, and because it is so, the temperature is so high, it is a gas. We also describe it as a pungent gas. What that means is that it has sort of a bad smell. It would be quite choking to the back of your throat, and bromine gas is actually toxic. So it's a red-brown pungent gas evolved. And the reason that I see that observation is because it is bromine gas that's being given off. So I simply need to think, what am I producing at the anode? Well, I'm forming bromine, and what does bromine look like? And that will be my observation. So the important things here are your half equation and your observations. At the cathode, what then is happening at the cathode? Well, I need to identify, first of all, what is my cation? What is my cation? And in this case, it is lead. And it is lead 2+, Pb2+. Okay, so I'm thinking to myself, how am I going to get from Pb2+ to just Pb? What do I need to do to get that back to an atom? Well, because it's Pb2+, that means it has 2 more protons than electrons. Or you can think of it as 2 less electrons than protons. And so I need to gain 2 to get it back to an atom. And that is our half equation for the cathode complete. It's just a lead ion gaining 2 electrons and becoming a lead atom. Again, I need to know my observations. And again, I need to just think, what am I producing? Well, my product is lead. What's lead going to look like? Well, it's a metal. And so how we tend to describe metals are they're shiny grey. Remember, we don't call it silver because silver is a metal in itself. So it's a shiny grey, and again we're going to see that actually the metal is a liquid. We know that metals tend to be solid, but because of the high temperatures used, it is a liquid. A shiny grey liquid formed. And why is it that is? It's because we're forming lead. That shiny grey liquid will be lead, and it sinks to the bottom. So if you can recall from the video we watched yesterday, when they poured the liquid out, you could see a little bead of metal at the bottom of the container, at the bottom of the crucible, and that was a little bead of lead. And we describe that as a shiny grey liquid that sinks to the bottom, or a shiny grey bead of metal. So that is your electrolysis for lead bromide, and we'll see a summary of that later. And the important things are your half equations and your observations for both the cathode, what happens at the cathode, and what happens at the anode. The next specific example that you need to know is the electrolysis of lithium chloride. The electrolysis of lithium chloride. And here is again a simplified version of what the electrolysis would look like. And we see that it's very, very similar for lead bromide. And we'll have a quick look at it now. So this is the example of lithium chloride. And again, the first thing I need to think of is what ions make up my lithium chloride. So the formula of lithium chloride is LiCl. My metal is lithium, which has the formula Li, and my non-metal is chlorine, which has the formula Cl. But I need to think about the charges that are on each of these ions. So lithium, I can tell because it is in group 1. Group 1 all form charges of 1+. So we use the formula Li+ for the lithium ion. And then the chloride ion, chlorine is in group 7, which all form an ion with a charge of 1-. And so it is a Cl- ion. So if we draw those into our electrolyte is going to be made up of lithium ions and chloride ions. And again, they are free to move about the solution or the liquid and move towards the electrodes. So again, we'll have the anode on the left, and we know that the anode is positive. So let's think, which one of my ions is going to be attracted to the anode? Well, it's positively charged, and so it's going to be the negatively charged ions that are attracted to it. And we also know that its anions go to the anodes. The anion here is the chloride ion, which has a formula of Cl-. Again, we're thinking kind of the reverse of bonding. What are we going to do to try and get that back to an atom? Well, because it's a negatively charged ion, it has an excess of electrons. What happens, just as with the bromide ion in the previous example, it loses an electron and gives it to the cathode. It loses an electron, and that means it becomes a chlorine atom. Overall neutral charge. It has lost its one extra electron that was making it negative in the first place. So let's think about an equation I can use to represent this. Well, I've had a chloride ion, and I've lost an electron, and I've formed a chlorine atom. But we know, again, that chlorine doesn't like to exist on its own, but it likes to exist as a diatomic molecule, Cl2. So if I'm going to form Cl2, I'm going to need to start with 2 chloride ions. And if I've got 2 chloride ions that are each losing an electron, I lose a total of 2 electrons. So that is my half equation that represents what's happening at the anode. What about the cathode then? The cathode, as we know, is negatively charged. Cathode is a negatively charged electrode. And so what's going to be attracted to it? Well, if it's negative, then it's going to attract the positive ions. And we know that cations go to the cathode. And so what is our cation here? Well, it's the lithium ion. So what happens is the lithium ions are attracted to the cathode, and they want to become atoms again. What does lithium need to do to become an atom again? Well, it's got one less electron than proton. That's what's making it positively charged. And so it gains an electron from the cathode. Once it's gained that electron, it becomes the lithium atom again. And it sinks to the bottom. So let's think about a half equation that we could use to represent this. So we've got lithium ions approaching the cathode. What they do when they get there to get back to lithium ion atom is that they gain an electron. Once they've gained that electron, they become an overall neutral lithium atom. And so that simply is the equation, the half equation for what happens at the cathode. One lithium ion gaining one electron to become one lithium atom. So let's write that into our notes on page 7. So in the electrolysis of lithium chloride, I first of all need to look at what's happening at the anode. So at the anode, it's going to attract the anions. What in lithium chloride is the anion? And we know that it is the chloride ion, Cl-. And just as we've looked at, the chloride ion needs to lose an electron to become a chlorine atom. But as we know, chlorine doesn't like to exist on its own. It exists as a diatomic molecule, which is Cl2. And in order for that to happen, we need 2 chloride ions, each losing an electron. And so in total, we're going to have lost 2 electrons. And don't forget the little negative charge when you're representing your electron. That's how we represent an electron in a half equation. So we've got 2 chloride ions, each losing 1 electron each. That's a total of 2 electrons. And that gives us our chlorine molecule, Cl2. What do we observe at the anode for lithium chloride? Well, again, all I need to do is simply think about what I am forming. This time I'm forming chlorine, and you need to think to yourself, what does chlorine look like? What is the appearance of chlorine? And we learnt back in the 3rd topic, periodic table topic, that chlorine is a yellow-green gas. Again, we're going to describe it as a pungent gas. And that just means that it's kind of a choking gas, and again, it is toxic. All of the halogens are toxic. So as a yellow-green pungent gas evolved. Why am I seeing that observation? It's because I'm producing chlorine gas. So at the anode, we have the chloride ions being attracted to it, losing electrons to become a chlorine molecule. And we observe that a yellow-green pungent gas is evolved. Moving down then to the cathode, well, first I need to identify what is my cation, and we know that it is lithium plus for this example. What half equation could I use? Well, I'm starting with my lithium ion, and I'm asking myself, what do I need to do to get back to an atom? With a lithium ion, we need to gain 1 electron, and it becomes a lithium atom. What do I observe at the cathode? Well, it's very, very similar than our previous example. Again, I'm forming a metal. Lithium is a metal. And so it's exactly the same observations here. I see a shiny grey metal in the form of a liquid because of the high temperatures. So it's a shiny grey liquid formed. Why am I seeing that? It's because it's lithium. And it sinks to the bottom. So again, I would advise that you learnt these observations for what happens at the anode and the cathode in both lead bromide and lithium chloride. But if you're able to remember your half equation, look to what you're producing, and that is what your observations will be for what is happening at the cathode. Over on page 8, you have a summary of the products, the half equations, and the observations of lead bromide, and the electrolysis of lead bromide, and the electrolysis of lithium chloride. You can see how they compare, and what I'd like you to notice particularly is for the observations at the cathode, they're exactly the same. You've got that beads of shiny grey metal formed. Moving our way up with the half equation at the cathode, you can see that always we have a positive metal ion gaining electrons to form a metal atom. Half equation for the anode, on the other hand, we've always got a negative ion losing electrons, we've got minus electrons, to give us a non-metal atom, which then join up together to form our diatomic molecules. Okay, you can see the product at the anode is always our non-metal, and the product at the cathode is always our metal. Then simply our observations for the anode, it depends on what non-metal we're forming, but we're just thinking about what that product is and what it looks like. This is something you need to learn, and from time to time it does come up on the 6-mark question. You would be asked to describe the process of electrolysis for one of the two, lead bromide or lithium chloride, and you'd be asked to include observations, half equations and products. So it's really worth learning this table. It's great if you can work out what is happening at both the anode and the cathode, and I'd like you to be able to understand that. And if you need to go over those clips of that part of the video explaining that, go over those again to try and reinforce that. But these are equations that you will be asked to quote, either in short questions or a long question. So make sure these two examples you're particularly familiar with. But moving on from that, not only do you have to know those specific examples, but apply that in order to predict the products at the anode and the cathode of a random ionic compound. And this is very, very simple. You just need to think that your non-metal anions, remember that non-metals always form a negative charge and metals always form a positive charge. So the non-metal anion goes to the anode. Non-metal anion goes to the anode. And so you can see the example of magnesium chloride. So the non-metal anion always goes to the anode. Well, what is my anion in this case? Well, my anion is chloride, which will form chlorine at the anode. Then at the cathode, I'm looking for my cation. My cation is going to be my metal, which is magnesium, and that is the product at the cathode. Let's do it for aluminium oxide then. So at the anode, I'm going to have my anion moving there. So what's my anion? Well, it is oxide. What is the atom I'm going to form from oxide? And you need to turn it back to its normal name, which is oxygen. And then at the cathode, my metal cation always goes there. And so at the cathode, I'm going to form aluminium. So have a go for potassium bromide and calcium chloride and see how you get on. Pause this video for just a second while you do that and then replay it again. So for potassium bromide, the non-metal goes to the anode, and that's going to be bromine in this case will be produced. And the metal goes to the cathode, and the metal in this case is potassium. Calcium chloride then, my non-metal is chloride, which is going to form chlorine. And my metal is calcium, which will form at the cathode. So what we're doing here is kind of the reverse of our equations for when a metal reacts with a non-metal. So take, for example, the first one. What we have is magnesium reacting with chlorine to give me magnesium chloride. That's how we would normally write this equation. But what we're doing in electrolysis is we're actually doing the reverse of this reaction. So we're taking magnesium chloride and we're converting it back to magnesium plus chlorine. And that's why I need to go back to my normal name, ending in INE rather than IDE. So you'll see a pattern here that at the anode, the product is always going to be the non-metal. And that is because non-metals are always the anions, and anions are attracted to the anode. With the cathode, the product will always be the metal. And that's because metals are always cations, and cations are attracted to the cathode. So if you're asked a question like this, don't be alarmed if it's an unfamiliar ionic compound and you think you haven't learnt what the products would be for that particular example of electrolysis. It's always the non-metal at the anode and the metal at the cathode. The last specific example you need to know of electrolysis is the extraction of aluminium, and this is an industrial example of electrolysis. So aluminium is a metal that has obviously got a lot of uses, both in our tinfoil for wrapping up our sandwiches, but also in more important things like aeroplanes. Aluminium is used for aircraft, and it's a really important metal, and so we need to be able to extract it So what we find it in nature is as bauxite. And we call that its ore. So the metal ore is called bauxite, and you need to be familiar with that name. You might be asked, what is the ore of aluminium called? In chemical terms, bauxite is hydrorated aluminium oxide. So basically, it's aluminium oxide, which is Al2O3. The hydrated part just means that it has some water molecules connected to it. And so what we want to be able to do is take aluminium from the ore. That's how we find it in nature, as aluminium oxide. And what we want to be able to do is split that aluminium oxide up into aluminium and oxygen so that we can get that aluminium and use it as a metal. So you might want to write that equation at the top. What we're doing is we're taking aluminium oxide and we're splitting it up into aluminium and oxygen. Simple as that. And we're doing that using the process of electrolysis. The process you need to be familiar with. Again, this could come up on a long question. They might ask you to explain the process of the electrolysis of aluminium oxide, including observations and any equations that are involved at the anode and the cathode. Okay, so the first step is that we need to purify our bauxite. Remember, bauxite is the ore, the aluminium ore. And we need to purify that to get rid of impurities such as silica, sand, and iron oxide. So iron oxide also exists in bauxite as well. Once we've got that pure aluminium oxide, it's still not what we want yet. We still want to take it from aluminium oxide to aluminium. What we do then is we dissolve it in molten cryolite. We need to dissolve it in molten cryolite. Again, you could be asked what that is. And we will see the reasons why we do that over in the next page. But it's basically to save money. And then finally, once it's dissolved in the molten cryolite, we're ready to carry out our electrolysis. So you'll see that the diagram looks very, very different for the electrolysis of aluminium. And you would never be asked to draw this. You may be asked to recognise it, but not to draw it. So actually, if you notice, the anodes are here. There's multiple anodes. Here are the anodes coming down here. So they look a different shape, and there are also multiple of them, and they're hanging down. Those are the anodes. Then you may ask yourself, where on earth is the cathode? Well, the cathode actually runs all the way around the outside. There's a gap here, and that's in order for the aluminium that we formed to be tapped off. But that is the cathode there. So this looks very, very different than our normal electrolysis apparatus. But you can see your anode and your cathode there now that they're coloured in. Okay, so again at the anode, ask yourself, what are we forming at the anode? Well, it's going to be the anion going to it. And what is your anion? Well, in this case, remember, it's aluminium oxide. And so your anion is the oxide ion. Oxygen has a symbol of O, and it is in group 6. All group 6 elements form a charge of 2-. So it's the anions, the oxide ions, that are attracted to the anode. And what they want to do is they want to get back to the normal atoms. What do I need to do to oxygen to get it back to the atom? Well, let's think about this. Oxygen has a charge of 2-. The oxide ion has a charge of 2- because it has 2 more electrons than protons. It has 2 more electrons than protons. And so what I want to do is lose those 2 extra protons. So represent that by -2 electrons. And that gives me my oxygen atom. But again, there's something not quite right about this, and that's because oxygen is a diatomic molecule. So again, just as we saw with bromine and chlorine, we have to actually produce O2. So if I want to produce O2, I'm going to need 2 oxide ions in the first place. And if each of those oxide ions is losing 2 electrons, then in total, I'm going to end up losing 4 electrons. 2 from each of the oxide ions. And so this is actually our half equation for what happens at the anode. We've got 2 oxide ions losing 2 electrons each, so that gives us a total of 4 electrons, reacting to give us our oxygen molecule. So it's a little bit more of a complicated half equation, but just build it up. Think about one oxide ion losing 2 electrons to get it to an oxygen atom, and then 2 of those oxygen atoms combining to form a diatomic molecule. And that's the overall half equation that we need to know. So let's think about our observations for what happens at the anode. What I'm forming is oxygen, okay? So always look at your observations as to what you're producing. I'm producing oxygen. So what does oxygen look like? Well, it's just simply a colourless gas. So what we're going to see, and you can see that in the diagram there, we see bubbles of colourless gas. And you're not as likely to be asked about the observations for this one. But again, it's just applying your knowledge and knowing that you're producing oxygen, and so I'm going to see bubbles of colourless gas being produced. That actually has an impact on my anodes, but we'll talk about that over on the next page. But before we do that, let's look at what happens at the cathode. Remember, the cathode is your negative electrode. If it's my negative electrode, then it's going to be positive ions that are attracted to it. So what are my cations? Cations in this case are my aluminium ions. Aluminium is in group 3, and that means it forms a charge of 3+. So the aluminium ions, they move towards the anode, and they need to become an aluminium atom. If they've got a charge of 3+, that means they have 3 less electrons than protons. And it wants to, in order to get to an atom, it wants to even that out. So in order to do that, each aluminium ion has to gain 3 electrons to become an aluminium atom. So whatever my charge is, I need to gain that many electrons in order to balance that charge out and allow it to become a metal atom again. And just as with lead and lithium, we see that those metal atoms, they sink towards the bottom, and they're in liquid form because of the high temperatures. And as you can see from the diagram, they sink to the bottom along here, and then they are tapped off at the bottom. There's that gap at the bottom where the aluminium is able to sink to and then flow out. And that's how we collect our aluminium, and obviously then it cools and becomes a solid again. So again, for this, you need to know your half equations most importantly, and know which ion moves to which electrode. So anode, it's always going to be the anion, in this case it's oxygen. And at the cathode, it's always going to be the cation that moves there. In this case is aluminium. So because this is an industrial example, and this is something that happens all the time, aluminium is widely used, as we've discussed. Because it's an industrial example, we need to know the industrial issues around it, both in terms of the cost and other issues involved. And the main issue with this aluminium extraction, getting aluminium from its ore in this way, is that it incurs a massive cost. It's really expensive to extract aluminium this way. And the reason that is because what I have to do is I have to take aluminium oxide, which is an ionic compound, and I have to melt it down before electrolysis can happen. Remember, I have to melt it down first so that my ions are free to move and carry charge and conduct electricity. So I have to melt that ionic compound down. We know that ionic compounds have high melting points, and so I need to heat it to a high temperature in order for this to get it molten so that it can conduct electricity. Once we're there at the point where it's molten, then actually passing enough electricity through the circuit to allow this to happen, that's a massive amount of electricity, which is also very expensive. So a lot of costs associated with this because of the high temperatures involved and the large amount of electricity involved. The second issue I touched on very briefly there, and that's at the anodes. If you remember, the anodes were shaped a little bit like this. And what are we producing at the anodes? Well, we're producing oxygen gas. So we'll just write O2 along here. I need to think to myself, what is my electrode made of? My electrode is made out of graphite. We know that graphite is carbon. Graphite is an allotrope of carbon. So what I've got is that my anode is made out of carbon, but at that anode I'm making oxygen. And what happens is that the oxygen produced at the anode reacts with the carbon in the anode and it forms carbon dioxide. What do we know about carbon dioxide? Well, it's a gas. So actually when we're producing this carbon dioxide, what is happening to the carbon is that it is wearing away over time. So I have solid carbon in my electrode, but when it reacts with oxygen, it forms a gas, and so obviously it bubbles away and is lost. And eventually over time we see that the anode wears away and we have to keep replacing it periodically. This still is a lot cheaper than using platinum as an electrode. We wouldn't have that same problem with platinum, but it would be very expensive. And so that's quite a common question actually. Why do the anodes need replaced periodically? And you need to explain that your electrodes are made out of carbon and you're producing oxygen at the anode, and those two react together to produce carbon dioxide. In your explanation, you would put this equation into words. You would say the carbon is reacting with oxygen to produce carbon dioxide. And this part here is also really important. The reason this reaction happens a lot is because you've got a high temperature. So it would naturally happen anyway over time, but because you've got a high temperature, it means this reaction actually happens more quickly than normal. And so we see this happening a lot. The carbon electrodes wear away over time, and so they have to be replaced. Okay, again, I touched on this on the reason that we add molten cryolite. And that's to reduce the cost of this whole process of the aluminium electrolysis. And what the molten cryolite does, this is step 2. Remember that the aluminium oxide, after it's been purified, is dissolved in molten cryolite. The first reason that we add the molten cryolite is that it reduces the melting point of the aluminium oxide. It reduces the melting point of aluminium oxide. If I've reduced the melting point of aluminium oxide, what that means is that I do not have to heat it to such a high temperature in order to get it in the liquid form. And remember, I need to put it in the liquid form, otherwise it doesn't conduct electricity. So if my melting point is lower, I don't have to apply as much heat energy in to get it to melt. And actually we see it has a massive difference. It reduces the melting point from 2050 degrees to 950 degrees. 950 degrees is still a pretty high temperature, but it's a lot less than 2050 degrees. So it reduces the melting point. I don't have to heat it up as much, don't have to apply as much energy to get it to melt. And the second thing that it does is that it increases the conductivity of aluminium oxide. It increases the conductivity of aluminium oxide. And think about the two things that give us a high cost. First of all, we have high temperatures associated. So we see how molten cryolite reduces that cost, because I don't have to put in just as much of a high temperature when it's dissolved in molten cryolite. But the second cost was because of the large amount of electricity involved. And if I increase the conductivity of aluminium oxide, that benefits the amount of electricity I need to use. I don't need to use just quite as much electricity because the conductivity is increased. So you may again be asked, why do you add molten cryolite during the electrolysis of aluminium oxide? And it would be for those two reasons. The second thing that happens to reduce the cost of aluminium extraction is that when we are doing this process, what happens is that the aluminium oxide that forms when it's slightly cooler at the top, it forms a solid crust of aluminium oxide. And what that has the effect of doing is keeping the heat in, rather than the heat being lost from the molten electrolyte. That solid crust prevents the heat from being lost and keeps the heat in, and so we don't have to keep applying just as much heat in order to get the aluminium oxide to melt and to stay melted. Obviously we have to heat it up to get it to melt in the first place, but we also have to keep it at a high temperature in order to keep it melted to prevent it from turning back to a solid. But that solid crust of aluminium oxide prevents heat loss and means I don't lose as much heat, and the heat stays in, and so I don't need to apply as much heat energy to keep my aluminium oxide a liquid. Something else you need to be aware of are the factors affecting where we place an aluminium extraction plant. So this is if a company was deciding to set up an aluminium extraction plant, these are the things they would consider before deciding where to do this, before deciding where to site this. And what I would advise with this is that you learn a couple of these, maybe 3 of these. I've never seen a question that is asked for more than 3, but you may be asked for these sort of factors, particularly in a long question. But it's things like large amounts of electricity being required, so we need to place it near a good electricity supply. Because we're adding in raw materials, we've got bauxite, that's the aluminium ore. It doesn't really make sense to place an aluminium extraction plant where there's no bauxite. If there's no bauxite there, I can't get any aluminium. So we need a good source of that. We need a good source of cryolite as well. The more local that source is, it cuts down the cost. So I need cryolite to dissolve my bauxite in, and also carbon for my carbon electrodes, and we've talked about how they need replaced over time, and so it's good to have your aluminium plant located in a place where there is plenty of carbon. Other things to think about is transportation links for the delivery of the materials, and then also to take the aluminium and the waste away from the site. We want good water supplies for washing, dissolving and cooling, and steam generation, so cooling the machinery. We want a local supply of people who can work at this aluminium extraction plant. And then also we need to think about the areas of conservation or outstanding natural beauty. We don't want to place an aluminium extraction plant anywhere near that would spoil those types of area. So again, learn a couple of those for going into your exam. And the very final part of this topic, you'll be glad to hear, is just looking at the idea of recycling aluminium. So this whole process of extracting aluminium is important because we need a good supply of aluminium. But something that we can do that is far better, far cheaper, is actually to recycle aluminium. So recycling aluminium only costs a fraction of the money that it does to extract new aluminium through electrolysis. So recycling aluminium is so important, and it doesn't only have the benefit of reducing the cost, but it also has the benefit of reducing carbon dioxide emissions. So if you think about our electrolysis, what is happening at the anode, just to briefly recap that, we're getting oxygen formed at the anode, and that our anodes are made out of carbon. That's then reacting with the oxygen that is formed to produce carbon dioxide. So over time, there's a lot of carbon dioxide released from this reaction. And recycling aluminium doesn't involve that as much. And so we see that we reduce the cost by recycling aluminium, but we also reduce carbon dioxide emissions. So we're saving money, we're saving energy, and we're saving resources. And finally then, it prevents waste from going into landfill. If I've got aluminium that I've used and I'm done with, I have 2 choices. I can either recycle it or I can throw it in the landfill. If I recycle it, it'll reduce that space taken up by the landfill. So there's some advantages there of recycling aluminium that you need to be aware of. So that's the topic of electrolysis finished. If there's anything you're unsure about, please go back and replay that section, particularly if you can get your head around what's actually happening in terms of the electron transfer. That would be great. And but the important things to know are those half equations and the observations for lithium chloride and for lead bromide, both at the anode and the cathode. And then the industrial implications of the extraction of aluminium using electrolysis. What I'd like you to do now is take some time and complete these questions in your purple workbook. That'll help you, now you've worked through the topic once, this will help you go back and reinforce that knowledge. And remember that you will need to know this topic for your mock on Thursday. So have a go at those questions and hope they go okay.